Okay, go.
Hi, my name is Jordan Smith-Jones.
Hi, my name is Candace Crossley.
I'm Shakira Key. I'm Nia Hubbard.
And we'll be presenting...
And I'm Kayla.
We are the Cheetah Girls. And we'll be presenting Chapter 3, Momentum and Energy.
Ooh, fancy. I like this.
So, what will we learn? What exactly is momentum and energy? What are the laws that come into play when dealing with momentum and energy? And where does energy come from, or does it disappear? All these questions and more will be answered as we explore Chapter 3.
Hi. I'm Nia. Once again, I covered Section 1, Momentum and Impulse. It can be thought of or described as moving inertia of momentum, that is. And the more the mass the moving object has, the more momentum it carries. Momentum is also a way to express how much force is needed to get something moving. The momentum of a moving object is the product of mass and velocity. It's also a vector quantity and has a mass times speed and the direction the object is moving. Okay. My first website for Section 1, it pretty much gives many keywords and examples of momentum and momentum as a vector quantity. As for website 2, it specifically has an interactive activity only for momentum, velocity, impulse, and kinetic energy. Okay. As for Section 2, impulse changes momentum. The product of the force and the time the force acts is known as the impulse given to the object. This impulse produces a change in the object's momentum. As for website 1, impulse of force in relation to momentum with mainly definitions and equations. And website 2 has many equations of impulse and its relation to Newton's second law is well explained. And the questions, a lot of them are based on basketball because impulse is easily related to sports.
Okay, Section 3, Conservation of Momentum. The law of conservation of momentum basically is in the absence of an external force, the momentum of a system remains unchanged. So basically, whatever momentum is lost by object 1 is gained by object 2. So if you're having a car crash like here, momentum will be lost by object 1 and be gained by object 2, which is this car right here. The first website I had, it was a very good site. It was interactive because while you read, you can click and watch animations and videos. And at the end of the lesson, there was a quick quiz to take to kind of test your knowledge. And the second website didn't have as much content to read, but it was still great because it showed you how the conservation of momentum really worked. It was an animation. You can kind of like toggle with the different masses and speeds of the 2 train cars that they had. Alright, Section 4, Energy and Work. Energy is a concept that is most central to all types of science. It is abstract, so it doesn't appeal to your 5 senses. Energy is the ability to do work or the ability to move or elicit change in matter. So energy makes things happen. And work is force times distance, or W equals F times D. For example, if I were to lift a box 10 feet in the air, I'm doing work.
Hold on.
The title here. So the interactive sites for Section 4, the first website I found, it was actually a game about energy and power. It was really fun, and I learned that energy doesn't come from thin air and that it doesn't disappear. And the second website was basically like a flip book, and you click the arrows to keep moving to different sections, and they had animations and games and a little quiz at the end, and that was a good website.
Hello, I had work energy theorem, and work energy theorem is work equals change in kinetic energy, and it emphasizes the role of change. The first website I found was an interactive website that shows a car with kinetic energy moving and stopping, and work was done on this car as it moved and the pulley pulled it down. And the second interactive website gave detailed information of what work energy theorem was, and it was followed by a quiz. And we can actually click on the first website so you can get an example of how it works.
You press Control and then click it on.
There we go. Yeah. So this kind of gives a little bit of information about work kinetic energy theorem. A weakness that I saw was it didn't really give detailed information about it, so I felt like that's what it should have done, but click the arrow. And the strength of this website is that you can, it's very interactive. It gives you, go ahead and click start. It gives you graphs, sort of like the Moving Man, what we did in chemistry lab. So it has the graphs and allows you to change the settings, so I thought that was a strength. Okay, you can go back. PowerPoint. And the next section is conservation of energy. Law of conservation of energy is energy that is neither created nor destroyed. It may be transferred from one form into another, but the total amount of energy never changes. Energy is either kinetic or potential. The first interactive website had a tutorial followed by a quiz to understand the concept. And the second interactive website had an interactive roller coaster where it showed it going back and forth from potential to kinetic energy, which you can click on the second website. Click launch. Hit play. So I thought this was really neat how it goes from potential to kinetic back to potential. So it kind of shows that energy is never, it's either created or destroyed, and it transforms from one to another. So it's never energy ending.
Oh, hi, my name is Kayla. My section was power. This section 7 is power. In this section, it talks about power and how to calculate it. Hold on. Did you put the...
Yes, I did.
Alright. Which is work overtime, which we talked about work in a previous section. The most interesting website that I found, it tells you that power has to do with the amount of work that you do over the amount of time that you spend working on it. Also, it said that each object or machine working on an object is different. So you can't have the same power for every variable because they're different. The website gives you 2 different formulas so that if you have a harder variables, you can still have a formula to work it out. The first formula is power equals work over time, or P equals W over T. The second one is power equals work over time, which equals force times displacement over time. Power equals force times displacement over time, which in the end equals power equals force times velocity. The website that I found. Did you not put my website?
I did. You have to click it again. Yeah, they're on there.
Okay. The first website that I found, it gives you precise definitions about what power is and their formulas. what I really liked about the website was that it gives you multiple examples afterwards. So after all of the reading through what power is, it gives you about five to seven different examples that you can calculate your own, and then you can see the example. At times it was like a little too wordy though, so you kind of got lost in the words. It was good in the fact that the formulas were like right there and bright so that you could see it, but it wasn't like really interactive like all the other websites where you could click on stuff. Website 2, in the website, it not only gives you like the definition, but also some history about power and where it came from. At first I was confused, but reading all of the material, I was a little less confused. I wouldn't really use this website versus the other website because
Well, got like, I think like 3 minutes left. Yeah, I think.
I'm almost there.
Okay.
Sorry.
Oh yeah, I didn't want to go over.
Section 8, machines. In this section, it talks about how you need power and work to operate a machine, and that these forces are important to each other. The website talks about how some machines work and some it told you how like examples were like how your toaster worked and how also like we as humans are machines. A really cool example is a steam turbine, which each part of it has to work and have the right amount of power, work, and force to have the whole thing work properly. And this was on the website, one of the websites that I found, and it pretty much is telling you the example was you as the machine is pushing, if the work of the broken cart, you have to actually work to get it to go straight. So you are the machine in this instance. In the first website, I really liked this website because it was very precise and had bold headlines. They told you about 6 simple machines and explained how they work in physics. It didn't really have any formulas and only described them a little. In the second website I found, it was really well thought out website, nicely laid out and easy to understand. It gave me formulas and examples, and it also had different links to explain work and power, and it also explained the examples of how they work, which was really nice because you really need to know the relationship between work and power to understand how machines work.
I had section 9, which is about efficiency. Efficiency is the percentage of work put into a machine that converts into useful output. The ideal machine works at 100%. Well, puts in 100% work of input and appears as work output. So basically, when you put in enough work, you can get out about the same amount that you need. Efficiency is expressed by a ratio, which is efficiency equals useful energy output divided by total energy output. I also had section 9 interactive sites was one from PBS Kids. It gave you a machine setup where you can figure out where you have to set up the machine and you have to figure out where the ball is going to land. So the ideal machine would operate at 100% efficiency. So this game lets students build an efficient machine to get the ball from one side to the next. Website 2 is an interactive game that lets students build an efficient machine, also using tools to get a ball to land in a cup. So you make whatever, or you use whatever tools you need to make it stay in one single cup. So the lever, like for an example of efficiency, a lever puts out 98% efficient, but wastes 2 joules of work input as heat. So you can definitely learn a lot from the 2 websites. I also had section 10, which was about sources of energy. The source of practically all our energy is the sun. Sunlight evaporates, rainwater flows into rivers and dams where it's directed to generators and turbines, then returns to the sea, and the cycle continues and is repeated. So that's basically how you get your energy. But a different type or a different way to produce energy is called electrolysis. Electrolysis is the electric splitting of water into element parts. how electrolysis works is that when electric current passes through conducting water, one end gives you oxygen and the other side gives you hydrogen. So that's what the bubbles form. So basically, electrolysis is just breaking the elements apart. The interactive websites I found for section 10 was the Science Museum. It's really stationed in the UK, so they have basically you figure out how to make your source of energy. So for example, they had the sun shines on a solar panel. The solar panel is connected to wires. The wires are connected to a radio, and the radio gives you music. So the question was, how can the sun create music? In those steps, that's all sources of energy. And the last website was a tutorial that just gives you the understanding of how electrolysis works. It allows you to see the calculations of electrolysis, and it allowed the students to pick different charges to see if it would complete the work or if it would complete to become a positive charge. And here ends our,
Are you done?
That's fine.
Energy, momentum, forces and work. And some of the stuff that's on the floor now. But how do they all fit together? First of all, work. What is work? Good, honest work. But how do we measure it? Well, work and energy are measured in joules. Work comes from force and distance. Remember how? Of course you can. That man pushing a rocket is pretty unforgettable. Well, it works like this. Here's a plot.
Hold on, text me what you said.
All we need to do is multiply the distance by the force.
Can you pause it?
Times 100 newtons.
I'm not really sure how to do that.
You just pause it right here. You should be good.
Yeah.
I just want. Did you pause it?
Oh, I didn't know how to do
I don't
it.
see him
Like that?
Yeah.
Okay, go ahead. You can press play.
And some forces and work. And some other stuff that's on the floor now. But how do they all fit together? First of all, work. What is work? Good, honest work. But how do we measure it? Well, work and energy are measured in joules. Work comes from force and distance. Remember how? Of course you can. That man pushing a rock image is pretty unforgettable. Well, it works like this. Here's a plot. All we need to do is multiply the distance by the force. So 3 meters times 100 newtons equals 300 joules of work. When you move a force over a distance, then you have done work. Now on to energy. Kinetic energy, potential energy, elastic energy, heat energy. Energy can change. A fast-moving bike wheel will transform its kinetic energy into heat energy pretty quickly if you brake suddenly. Next, pork pies. You can use a grapefruit if you're on a diet, but there's no real reason to, as we're not going to eat it. The point is to lift an object off the floor and put it on a shelf. Why not? It takes some work to lift the pie against the force of gravity. This work gets transformed into gravitational potential energy. That's the energy that would be released if it fell. If it fell. When it swings, 2 forms of energy are transformed back and forth between each other. But how do you know which? When you pull the ball on a pendulum out to the side, it moves up too. It is higher up, so it has gained gravitational potential energy. Remember the pie. Same principle, but less messy. Now we let the ball go. What happens to the energy? Well, as it falls, it loses height, so loses gravitational potential energy. But it starts moving faster and faster, so it gains kinetic energy. As it swings back up higher, it gains gravitational potential energy again. But also, as it swings up, it slows down and loses kinetic energy. Over and over, the energy is transformed back and forth. Gravitational potential energy to kinetic energy. Each swing will be slightly less than the previous one, as some energy is transferred to the surroundings, mostly as heat, but not much heat. Kinetic energy isn't just for pendulums. Anything moving has kinetic energy. It's all about mass and speed. Kinetic energy equals half mass times velocity squared. Velocity, of course, is speed. Suppose a 1,000 kilogram car is travelling at 10 meters per second. That's 36 kilometers per hour, by the way. Go granny. The car's kinetic energy is given by half the mass times the speed in meters per second squared. So that's half times 1,000 times 10 times 10. So that's 50,000 joules or 50 kilojoules. It all makes so much sense. Now, momentum. What is it? Momentum is also about mass and velocity, but its formula is simpler. The momentum of an object is its mass times its velocity. The more mass you have and the more velocity you have, the more momentum you have. Now, if you lose that momentum quickly, you will feel a large force. Lose momentum more gradually and you'll feel less force. There's another thing about momentum you need to know. When something explodes, its total momentum before is the same as its total momentum afterwards. And also in collisions and crashes. Let's look in more detail at the cannon. Total momentum before the gun fires is 0. Nothing is moving. After it fires, the cannonball is moving forwards. That's momentum in a forwards direction. The cannonball has small mass and large velocity. Momentum in the backwards direction will cancel this out. The cannon recoils backwards. It has large mass but small velocity. The two objects, cannon and cannonball, have equal momentum in opposite directions. They cancel out. That keeps the total momentum equal to 0, which is why we get recoil when guns fire. And how jet engines work, how rockets fly, and how balloons do their thing. Not that you're ever going to get to see all that at once, unless you go to a NASA-sponsored military-themed jet pilot birthday party. But you never know.